Hi, I'm Brendan Byrne. You're probably wondering why this episode is a bit late. Well, a little bit of background about me. I'm a journalist with WMFE, and I'm based out of Orlando, Florida. And as I'm sure you know, tragedy struck this city. And as a journalist representing this community, it was my job to jump into breaking news coverage. And that gave me little time to work on this podcast. Well, since then, things have settled down, and the city's moving forward, and this newsroom is moving forward, looking to find out how the community will move forward. But that gives me a little more time to come back to this podcast. But before we move on, I do want to give a very special thank you to those folks that reached out to me, knowing where I was and knowing where my job was, and letting us know that Orlando was in their thoughts. Thank you. But now, let's get back to exploring space. From the studios at WMFE in Orlando, Florida, this is the Space Exploration Podcast, asking the question, are we there yet? Thanks for listening. I'm Brendan Byrne. Right now, the Juno spacecraft is flying towards Jupiter. In just a few days, on July 4th if you're here in the U.S., July 5th if you're overseas, Juno will enter orbit around our solar system's largest planet. It's been 5 years since Juno launched from Cape Canaveral. And once it enters its polar orbit, we're going to learn so much about the makeup of the planet, as well as key scientific findings that will help us better understand how planets and solar systems form. And to better understand this mission, I reached out to someone who's been following Juno all throughout the spacecraft's journey. Well, joining me by Skype is Emily Lakdawalla. She's the Planetary Society's senior editor. Emily, thanks for joining me.
Thanks for having me.
So let's start with what we do know about Jupiter. So bring us up to speed on what we've learned from, say, ground-based observations and the Galileo spacecraft.
Well, number one, it's big. It's the biggest thing in our solar system other than the sun, and it actually has a lot of similarities with the sun. It's made of much of the same materials and very, very similar proportions, but it's not big enough to ignite thermonuclear fusion, so it behaves more like a planet than a star. And we're trying to understand what's going on in the deep interior that is different from a star and sort of intermediate between stars and planets.
And what kind of scientific impact is that going to have?
Well, it has a lot to do with our understanding of how solar systems form. It kind of gets at the question of how did we get here in the first place? How do you begin with a nebula of gas and dust and make suns and make planets? And then how do those planets influence the formation of all of the other little tiny bits of dust in the solar system, which is what the rest of us are made of?
And what do we know about how something like that comes together in a solar system? What have we learned so far from the Galileo spacecraft?
Well, the Galileo spacecraft was a mission that was sent to orbit Jupiter, and it was intended to answer a lot of these kinds of questions about Jupiter. But unfortunately, the Galileo mission was hampered by the fact that its umbrella-like main radio dish never unfolded. So the amount of data that we got back from that mission was really small. We learned some things about its magnetic field. We learned some really important lessons about what we need to do to build spacecraft so that they survive in Jupiter's really nasty radiation environment. And those lessons have been applied to Juno. And now we can use Juno to study the deep interior of Jupiter with instruments that are very different from the kinds that Galileo had.
So go ahead and walk me through the Juno spacecraft. What's this thing look like, and what scientific instruments are on board?
All right. To begin with, Juno is a really big spacecraft, but most of its size is in solar panels. The solar panels are absolutely gargantuan. There's 3 of them arrayed in sort of a triangle shape around the spacecraft, and the center part of the spacecraft is a hexagon. The whole thing rotates rather slowly, about 2 times per minute. And spacecraft rotate in order to make them stable. It helps them navigate spacecraft very precisely. Now, on top of the hexagon center of the spacecraft, there's a vault. It is a titanium-walled vault that contains all of the sensitive electronics for all the instruments because, like I said, Jupiter's radiation environment is really, really nasty. It has a very powerful magnetic field. That magnetic field accelerates charged particles and electrons to very high speeds, and those particles run around and slam into electronics. They cause damage to the electronics. They can flip bits in the computer memory and generally wreak havoc with the program. So that's why it's important to put all of your electronics inside as much much protection as you can muster, and that's what the titanium vault is for.
And this is what we learned from Galileo, right?
This is one of the things we learned from Galileo. We learned some details about how the magnetic field is structured, and we learned how Juno is going to be able to try to avoid most of that. Part of it was with shielding, but part of it is with a very clever orbit. So Juno is going to have this polar orbit, and a polar orbit is great because it allows you to sample parts of the environment that we've never sampled for Jupiter before. Most spacecraft have passed by its equator. So it's interesting scientifically to look at Jupiter's poles, but it also just happens that by orbiting in this polar orbit, you actually fly the spacecraft through a donut hole in Jupiter's magnetic field that actually helps you avoid the worst of it. And so that's the key to Juno's survival, is its ability to fly in this polar orbit that avoids the nasty radiation environment.
That's really cool.
Yeah, unfortunately, it won't last forever. And the reason is because Jupiter is not a sphere. Jupiter is flattened because it rotates fairly quickly. And that flattened bulge of Jupiter exerts a non-spherical gravitational force on the spacecraft. And what that means is that it's pulling on the spacecraft in a way that's going to change its orbit. So the orbit shape will stay the same, but the orbit's orientation, it's going to tilt over time. And as the orbit tilts, it's going to dip it slowly deeper and deeper and deeper into the nasty magnetic field. And that's what's going to kill the spacecraft eventually.
So we talked about that titanium dome that kind of protects those sensitive components. What other instruments are on the Juno spacecraft?
Well, most of Juno's instruments are designed to look underneath the cloud tops that are the most dramatic thing you can see on Jupiter. So, for instance, it has these microwave radiometers, and all that means is that it's looking at electromagnetic radiation that has long wavelengths, microwave wavelengths, as opposed to the very short wavelengths of visible light. And those long wave radio, radio can travel very long distances without getting blocked or scattered. And so we'll be able to see these radio emissions from deep inside Jupiter and be able to see how the cloud and atmosphere, how its behavior changes as you go deeper inside Jupiter's atmosphere. But even that is only going to sample a little bit of Jupiter's skin. So you have other instruments that are designed to study things like the magnetic field, which we think probably originates much deeper inside Jupiter. There's a magnetometer. There's these plasma waves instruments, which don't ask me how to explain those. I'm a geologist. I'm not exactly sure how they work. And then there are instruments that look at the aurora of Jupiter, which relate to the magnetic field and how that interacts with Jupiter's atmosphere.
So it's my understanding that there's this microwave sensor on there that's looking at the gravity of Jupiter. What are we going to learn from that?
Well, we actually look at gravity on planets with every single spacecraft that we use to explore all over the solar system. We don't do that with a sensor that's on the spacecraft. We actually do it by tracking the radio transmissions between the spacecraft and Earth. So every spacecraft has a big dish antenna, and they all communicate with Earth using these gigantic dishes of the Deep Space Network. And by tracking the positions of the spacecraft, the frequency of their transmissions, the Doppler shift of the transmissions, we can understand the position of the spacecraft in space to a really unbelievable level of detail. And so as we track the spacecraft, we can see them speed up and slow down by minute amounts. And the minute amounts that they speed up and slow down are controlled by the particular shape of the gravity field around a planet. And so if you have a planet where its mass is more concentrated in the center, then the spacecraft will feel a tug from that center mass when it's closer to the planet. But if the planet's mass is more kind of evenly spread throughout its interior, then the spacecraft will feel that tug a little bit earlier. And so by combining all of the radio tracking information and involving a supercomputer, usually, they can figure out how mass is distributed, how much it's concentrated toward the center. And sometimes for funky worlds like asteroids, you can even map out interesting concentrations of mass here and there in different places on the planet. We don't expect to see concentrations of masses in Jupiter. What we're really after is understanding how dense its very center is, whether there's something kind of like an Earth buried deep down there. Maybe there's something even much bigger than Earth buried deep down inside Jupiter. And we'll do that with this radio tracking.
This has been a 5-year journey for the Juno spacecraft. Can you kind of tell me about how it's getting there, and what we can expect when it makes that initial entry burn on July 4th.
Well, Juno, like a lot of deep spacecraft, took a longer path than a direct route to Jupiter because you can save some money by launching it on a smaller rocket, having it go around the sun at least once, and then fly by Earth to get a boost on its way to Jupiter. And that's what Juno did. And so now it's had this long cruise. It flew past Earth once, which is kind of cool because you get to test out your instruments on a planet by doing an Earth flyby. And then now it's getting close to Jupiter. It's actually close enough to Jupiter that it's passed by the orbits of some of Jupiter's outer moons. And on the night of the 4th of July here in the U.S., it'll be July 5th if you're in Europe, it's going to pass close to Jupiter and then start firing its rocket. It has to fire its rocket for 35 minutes continuously in order to get the orbit that they want. It has to do at least 20 minutes of rocket firing in order to successfully enter orbit at Jupiter at all. If it doesn't do that much, then it's going to shoot past Jupiter, stay in a solar orbit, and never be able to get back. So this is a really crucial moment for the mission.
That burn basically slows it down enough for the gravity of the planet to pull it in, right?
Exactly. Yeah, you think about rocket burns as speeding something up, but when you're traveling farther away from the sun, the planets are moving much more slowly in their orbits farther from the sun than Earth is. And Juno started out with Earth's orbital energy. So you do have to slow down the spacecraft in order for Jupiter's gravity to be able to capture it into orbit.
Now, it's also my understanding that there's these really, really cool science, instruments on there that really are only readable to science folks and astronomers like that. But there's also a camera on board, right? Can you kind of tell me a little bit about that and what pictures we're going to be seeing from the planet?
Sure. The Juno mission was a mission, designed to look at the deep interior of Jupiter. But I think everybody agreed that you can't send a spacecraft to Jupiter without a camera. It would be a crime if you did that. You have to take beautiful photos while you're up there because it's the most spectacular planet in the solar system for its colorful belts and bands. And so they put on a small camera. It's not a science instrument. It doesn't have stated scientific investigations, and that actually isn't guaranteed to survive for the entire length of the Juno mission. But it is based on science instruments that have been developed for other missions, Mars missions actually, and it's a really wonderful color camera called Juno Cam. It's mostly designed to take photos when Juno is quite close to Jupiter. Its field of view has been set so that whenever Juno is close to the poles, it can take a photo of Jupiter where you see the entire planet inside the camera field of view. And no other spacecraft has really done that. One of the Pioneers got sort of polar views of Jupiter, but this will really be the first high-quality modern camera images where you're not looking at Jupiter equator on, you're looking at it down from the poles, and we'll really see a lot of these polar details in detail for the first time.
Now, is this going to be like New Horizon where there's going to be a bit of a lag time between the photos being taken and the time they get back to Earth and processed?
Well, there's always some lag because these spacecraft aren't in continuous communication with Earth. But talking with Jupiter is not nearly as hard as talking with Pluto. Jupiter is about 5 times Earth's distance from the sun. Pluto is more than 30 times Earth's distance from the sun. And radio signals get weaker as the square of distance. So it's far away, but it's not that far away. And the data rate from Juno is not going to be too bad, especially given the size of its antenna. So we should be able to see JunoCam images within a day or two of their capture.
Oh, wow.
And yeah, we'll be seeing them right away. There won't be as many images because it's a camera that's there only for public information, and so it'll take some cool pictures, but it can't take up a ton of the data rate. We've got to give the bandwidth to all of the reasons that the spacecraft is actually there, but its images are going to be really cool.
Now, I'm not an astronomer, but I know there's pretty much zero chance of us finding evidence of life or anything on Jupiter. Really, what's the overall scientific significance of this mission?
Again, it's about understanding how solar systems form, how planetary systems form, how we get giant planets. Because, these days especially, we're discovering all of these planetary systems around other stars. And some of them look somewhat similar to our solar system, but most of them look really different. And so understanding how all of those other solar systems came to be, in order to do that, we have to understand how our own solar system came to be. So it's really about answering all these fundamental questions about how we got here and why we're different and how we're the same as other stellar systems.
Now, how long will Juno be on this mission, and what happens after its mission's completed?
Well, Juno will be orbiting Jupiter throughout 2017 and into the very beginning of 2018. But that evolution of its orbit that I talked about is going to really attack the spacecraft's electronics and make it difficult for the spacecraft to survive. So they've actually planned the death of the spacecraft in February of 2018. They're going to do a rocket firing sometime before then, I think sometime in 2017, that will make the orbit one that over time gets closer and closer to Jupiter's cloud tops. And so we already know the date of Juno's death in 2018. It's going to plunge into Jupiter. I believe it is going to be transmitting the whole time. So we'll be able to continue to get information from the science instruments all the way down until the mission is over, which is really super.
That's kind of different than a lot of these other missions we've been seeing, like Kepler's gone into a secondary mission. This one's, when it's done, right?
Absolutely. When it's done. We know the death date of the mission. We got to get all the science we can out of it before that happens.
Emily Lakdawalla, what are you most excited about learning from this Juno mission?
I can't deny that it's going to be the images that I'm really most excited about.
Me too.
Because those images, they're going to be so beautiful, and we'll be able to see cloud dynamics up close, especially these polar views, in a way we've never been able to do before. One of the wonderful things about this public camera is that it's being supported by amateur astronomers all over the world, taking lots and lots of photos of Jupiter. It's not just the Juno data set. We're also going to have this really rich data set covering Jupiter practically continuously for a year and a half, so that atmospheric scientists are really going to have rich data in order to understand what's going on with Jupiter's belts and zones, what drives its clouds, what changes its weather, why the red spot is shrinking, how things change so quickly. It's going to be wonderful. It will take a while. The science is going to take a while to understand. It'll be years, even after the death of Juno, that we'll be seeing new scientific results coming out of it.
And those images, they're really so important to get public interest, drummed up for planetary science, right?
Absolutely. It's the images are really what it's all about, and it's just wonderful that NASA shares this data with the public and allows people to ride along with the mission.
Where are you going to be July 4th when it enters the orbit?
I will be at the Jet Propulsion Laboratory in a room with lots of other members of the media, watching and listening to the mission control talking about the events on the spacecraft and hoping that everything goes well.
Well, be sure to follow Emily Lakdawalla on Twitter. You reached 100,000 recently, so congratulations are in order. But she'll be tweeting it, I'm sure, the whole time, and there's always great stuff coming from Emily and the folks over at the Planetary Society. Emily Lakdawalla, she's the Planetary Society's senior editor, joining me by Skype. Thank you so much, Emily.
Thank you.
That's it for this episode. Support for Are We There Yet comes from the listeners of WMFE. You can follow the show online. We're at Twitter, at AWTYMars, or reach out to me in the Twitterverse. I'm at Space Brendan. Leave us a review if you listen on iTunes. That's how more people learn about the podcast. Are We There Yet is a production of WMFE. Our theme music was composed by Kevin McLeod. Production assistance from Adam Mano. Find more space news online at WMFE.org/space. I'm Brendan Byrne. Thanks for listening.